Is Alejandro Weinstein talking about a tale of 4 libraries.
Thank you. Thank you for being here. Today I'm going to talk about how we are using 4 different libraries in our research. In particular, I'm going to explain how we are building this figure. I'm going to give you more details later, but broadly speaking, these are Wikipedia articles, and you can observe the articles and the links between the articles, and the size is proportional to the similarity between this original article and remaining ones. So, as a very general motivation for my talk is that NumPy is not only an effective way to compute things in Python very fast, but it's also a de facto standard for different scientific libraries. And because different libraries speak the same language or they use the same data structure, they can communicate between each other in a very convenient way. So the problem we want to solve is how to learn to navigate in a linked data set. In particular, we know that many times it's hard to find, to know how to navigate. Like if you go to Wikipedia, you start in some articles and you want to find other articles that are related, and it's very easy to get distracted and go into articles that are very different than the original one. So can we design an agent able to automatically learn how to navigate in a linked data set like Wikipedia or another one? And to make the example a little more concrete, say you just read this book, you want to know more about its author, James Blake, you go to this Wikipedia page, and now you see all these links, and where do you click here such that you go to other articles that are similar to James Blake? So that's the problem we want to solve in general terms. How we want to solve it? We want to solve it using reinforcement learning. Reinforcement learning is a framework inside artificial intelligence where you have an environment described by a Markov decision process where you have an action as an input, and the environment is going to react to this action with a new state and a reward. And the agent is going to observe this state and the reward, and its task is to decide what's the new action to take. And the objective for the agent is to have what is called a policy, which is a function between the state and the action, such that the sum of all this reward over time is maximized. So this problem is hard in general because of 2 reasons. One, we in general we don't have a model for this environment. We need to learn it through experience. And the second reason why solving this reinforcement learning is hard is because we say that things need to get worse before they get better. Like in this Wikipedia example that we have, we think sometimes you need to click in some links that initially looks not very related to the original one, and later you are going to find some articles that look more interesting or related to the original one. So that's why we think reinforcement learning, because it's able to handle these kind of problems, is a good tool to solve what we want to solve. So the first library we use for solving this is RLGlue. This is a nice library because if you look at this diagram here, it looks very similar to the diagram in the previous slide. It means to write a reinforcement learning problem using this library, you just need to write these 3 programs. And one is for the agent, the other one is for the environment, the same as in the previous slide. And the only extra piece is you need to write this experiment that is just a program that is going to coordinate the execution of these 2 different programs. And here the 3 examples are in Python, but another nice thing about this library is that you can combine programs written in different language, or maybe some third party wrote an environment maybe in Java or another language, and you can write your agent in Python. And writing the actual code is also simple. Here I have like the skeleton code for the environment. You need to write a function that returns the current state when it starts. And then you have the second function that is execute every time you have a time step. and you observe an action, and this piece of code needs to return the next state and the reward. On the other hand, the agent is going to, in the first iteration, observe the state, and it needs to return the action, and in the next steps, it's going to observe the rewards and state, and it needs to return the action. Of course, the hard part is to figure it out what to put inside this block such that as you observe different states and reward, you learn how to compute this policy that is maximize the sum of all these rewards. And the experiment is very simple. You just need to initialize everything. You start, and then you run an episode with so many steps. And in addition, I'm not showing this here, but there is also a mechanism to communicate these different pieces. So after you run these 100 steps, for instance, you can, from the experiment, query the agent and do some post-processing and analyze your data. The second piece we need to solve is how we are going to compute the reward in this reinforcement learning problem. And for the case that you're working with documents, we are going to use what is called the latent semantic analysis. So the idea here is you have two pieces of text, and you want to compute how similar these two documents are. So to build this model, you start with a set of documents. Say you have n documents. The first step is to build a dictionary with m words. You need to fix this m to, say, 10,000 words. Once you have this dictionary, for any document, you can build a bag of words representation where you have the frequency. For instance, a document may have 5 times the first word, 8 times the second word. It doesn't have the third word, and so on. But this model is not very meaningful because just the frequency is not enough to get a good representation. So better representation is the term frequency inverse document frequency representation, where we multiply the frequency for each term in a document by the logarithmic of the inverse frequency across the whole set of documents. So this has a more meaningful representation of a word, but still we can do a little better by building this LSA model. So to build this model, we build this matrix C where we stack all the documents in an n by n matrix. We compute the singular value decomposition. Then we fix K, typically in the low hundreds, say 200s. And you build this low rank approximation of this C matrix. And once you have this C matrix, you can project any vector in this TF-IDF model onto this LSA model. So in summary, you start with a document, you build this bag of words, you project onto the TF-IDF, and then you project onto the LSA. So you start with a document that is very large, and you end in a vector of dimension k. Now this seems very easy to do. However, for big numbers of m and n, computing this singular value decomposition is non-trivial. You cannot just go to any linear algebra and compute SVD of C because it's too big. So we need something sophisticated enough to build this latent semantic analysis model. So we use this library called Gensim that is able to handle this. It's very straightforward to use. You build the dictionary, then you build the bag of word representation of your corpus. You build the inverse frequency representation. You build the LSA model. And once you have that, you can, any query, you can transform it to the LSA model. You apply this tree transformation, and you can compute the similarity just by computing the angle between these two vectors. And it's important to note here that some Gensim outputs or works with NumPy arrays, so it's very easy to take this output and connect it to any other library that knows how to handle NumPy. And it's also interesting to mention that Gensim is very good at handling this big data set. So as an example, to test the library, I took the 100 most popular books in Project Gutenberg, and then I took Moby Dick, the whole book, and compared the similarity between a piece of Moby Dick and the article of the Wikipedia about Moby Dick, and then 3 other articles or pieces of text that are unrelated. And if you look at the similarity, you're going to see that for pieces of text related to Moby Dick, you get very good numbers. This is a cosine similarity, so the numbers are between 0 and 1. So you get good numbers for things that are related to Moby Dick and low numbers for things that are not. In terms of efficiency, building this model is quite time-consuming. With a single core, it takes almost a day to compute it. Gensim also provides mechanism to use multi-core, and you can do it in a few hours if you have enough machines. But the good thing is that once you build this model, you can you can project onto the LSA space very fast, in the order of 10 milliseconds. So it takes some time, but once you have the model, it's very efficient. And the next part that we need to solve is how to represent the state space, and it's very natural to use graph to do that. And for that, we use Network X, which is also a very nice library. It's very Pythonic. In particular, we can use any object that we can compute the hash as a node identifier, and any object as a node or edge or graph attribute. So we can use the LSA representation, for instance, as a node attribute without problem. So it's very easy to connect these two things. So with all these ingredients, we can run some experiments. This is a simple experiment, also using simple Wikipedia, which is a version of Wikipedia with a lower complexity. So in this experiment, we are taking 100 articles. We start with Army, and we collect in a breadth-first way 100 different articles. And then we compute the LSA representation for each of these. And in this plot, the size is proportional to the similarity. So you see some of them are very unrelated to the original one. And the interesting thing is that more than one click ahead, we find some things that are very similar to the original one. So someone clicking is kind of hard to click from Army to Soldier, then to Gun, then to Defense, to find this one. This one is a simple example, but in the next one, we're going to see that it's much harder. So this is the same kind of experiment, but now with the whole not the original Wikipedia. We start with James Clegg, and we grab 2,000 articles. And in red are the 10 most similar articles to the James Clegg. And you can see how many of them are more than one click ahead. So in this original problem that we want to solve, we are validating our idea that there are articles that are similar to the original one, but they are relatively hard to find. I mean, in this whole graph, it's very hard to say that someone is going to, starting from here, click in Richard Feynman, and then click in this, any of these guys who are quite similar to James Clegg. Or like this Robert Wright, you need to click, it's hard to see here, but you need to click in the Slate magazine article, and then from there you go to Robert Wright. So I mentioned initially, we are working in problems that you need to get worse before it gets better. Like the Slate magazine example is a good one, because it's not obvious that by clicking there, you're going to find an author that is very similar to James Clegg. And this is obviously not solving the whole problem. Then this is a work in progress, but this experiment is somehow validating our hypothesis that this is a problem interesting to solve. And to finalize, the fourth library we're also using is scikit-learn. For reasons I don't have time to explain, we think it's a good idea to use the LSA representation not only for computing the similarity, but also for representing the state. Now, to validate this idea, we are using a technique known as isomap that allows to reduce the dimension of a vector, in this case from 200 to 3, so we can plot it. And here I'm doing this with a few articles. I'm plotting them in this R3 isomap representation, and I'm overlaying the links between the article. And you can observe how the articles are located in regions related to the semantic of their semantics. So we are finding that the LSA, even after this huge dimensionality reduction, is still meaningful. And it's also interesting to see that although they are similar, many times there is no link between them. So you need to learn how to go from one article to another, going through some regions of the space that are far away or farther away. So with this, I finish my presentation. If you have any questions.
If you have questions, use the mic over there.
How might this apply to improving the efficiency of various search engines? And in particular, if the clustering indicated in one of your screens is meaningful, it seems to be clustering in a way that in an aggregate is not simply connected. So if one were to try to trace a path, one might have to make a choice among multiple paths, not all of which might be efficient.
So we think it looks at least superficially similar to like what you do when you go to Google, but the problem is different because if you go to Google, you need to know the search term you are looking for. But what if you are looking just for a theme? You don't know exactly. Like if I go and type James Blake, I'm going to get a lot of results from James Blake. Except, well, now Google recently released a new functionality that does something very similar to this, but using a different mechanism. But traditionally, you just get things similar to a query that you type. So it's a different problem than that. So we don't think this is going to help to typical search engines, but to be a different way, a way to solve a different problem. And regarding the second part of your question, well, we think this reinforcement learning formalism should be able to handle what you were saying. I mean, through this learning part, you should be able to somehow the agent is going to learn this topology of the state space and learn how to go from one part to the other, maybe taking the right decision or things that look reasonable for him. But as I said, this is a work in progress, so we are still seeing if this is going to work out or not as we want.
Do you plan on publishing this methodology? And there was a lot of information, a lot of steps you took in there.
Well, we have a paper submitted to this conference.
Oh, okay.
So
thanks.
There is more than, I mean, everything that is here is in that paper. And at least I promise that I'm going to release the code for that. So you should be able to reproduce everything I showed here.
Questions? No, let's thank our speaker again.